So Shukun, please.
Oh, okay. Okay, thanks, Jessica, for the invitation. This is a joint work with Shengwen and Changkeun. Yeah. Okay, now let's get started. We first take a look at the Bochner Riesz mean. So for any factor lambda greater than 0, we define the Bochner Riesz mean of all the lambda as the following. So basically here, this guy is a summation function phi t dtx. So, okay, why can I continue? Okay. So in the Bochner Riesz mean, the summation function is taken as this guy. And this guy can be considered as a modified version of the ball mean, so-called ball mean. So where the summation function for the ball mean is the characteristic function of the unit ball. So the factor lambda here is actually a regularity factor. The bigger the lambda, the better regularity condition you have on phi. So in some sense, Bochner Riesz mean is like a better mean than is a better function than the characteristic function of the unit ball. Okay, and yeah, we can use the Bochner Riesz mean to study Fourier integrals. So basically, for any factor lambda greater than 0, we define this this partial sum T lambda TF as the following. And a question we would like to ask is when does this partial sum converges to F almost everywhere, or when does it converge in LP? Okay, now let's first take a look at the almost everywhere convergence problem. So yeah, when P is greater than 2 F in LP space, we have the following theorem by Carberry, Ruby, Differentia, and Vega. I think this theorem is proved in 1985 or so. So basically, it says that for any LP function F, the partial sum converges to F almost everywhere when P is in this range, and the upper range P lambda is given by this formula. And a little remark here is, yeah, this result is sharp for the endpoint P lambda. So basically it says that when P is greater than 2, then the almost everywhere convergence for Bochner Riesz mean is completely settled. Yeah, however, when P is less than 2, the problem is much harder. And in order to answer this question, let's first introduce the Bochner Riesz operator. So basically, in the partial sum, we are taking the radius t to be 1. So the Bochner Riesz operator is defined as the following. And we can also define the associated maximum operator. So basically, the maximum operator is taken to be the supreme of all the partial sum. Yeah, by Stein's maximal principle, when P is less than 2, if all this operator T lambda T is bound in LP space, then these two statements are equivalent. So the first one is that the partial sum converges to F almost everywhere, or converges almost everywhere. The second one is that the maximum operator is found in weak LP space. So as a result, to understand the pointwise convergence of the Bochner Riesz mean, we only need to study the maximum operator. And before that, we should notice that here is a prerequisite is that all this operator T lambda T is found in LP space. So we kind of should understand all this operator first. And after dilation and modulation, they all are reduced to the Bochner Riesz operator. So there's a reason why we should understand Bochner Riesz operator first. And somehow the LP convergence problem of the Bochner Riesz mean can also be reduced to the boundness of the Bochner Riesz operator. So it is quite natural to study the Bochner Riesz operator. Now for the Bochner Riesz operator, there's a conjecture named by Bochner Riesz. So we define a factor lambda MP as the following. Here's a little remark. Lambda MP would greater than 0 if P is greater than 2n over n minus 1. And this is just the sharp exponent for the Fourier restriction conjecture. So as you can see from this, Bochner Riesz problem and the restriction problem, they are closely related. And the conjecture is that the Bochner Riesz operator is bounded in LP space when lambda greater than the endpoint lambda MP, which means that the regularity lambda has, the regularity factor lambda is greater than the minimum possible, which is lambda MP. And the endpoint is sharp and is given by the following example. So we basically take the asymptotic expansion for the kernel. So this is basically the Fourier or the kernel of the Bochner Riesz operator. So we do asymptotic expansion for this guy. Let's call it m lambda. Then m lambda has the following expansion. And if we take a test function f such that its Fourier transform equals to 1 on the unit ball, then when it composed with the Bochner Riesz operator, T lambda f would just be m lambda. And the fact that m lambda is bounded in LP space, I mean, this guy is bounded in LP space if and only if lambda greater than the endpoint lambda MP. So that's the reason why the endpoint is sharp. Okay, now let's introduce our main target today, which is the square function. So in around the 1950s, to study the Bochner Riesz operator and its associated maximum operator, Stein introduced the following type, little with the pilot type of square function. And this formulation may be a little bit complicated to digest. And later we give you a more clear version to understand it. Yeah, so it is conjectured that the square function is bounded in LP space when lambda greater than an endpoint lambda MP prime, and when P greater than 2. Note that lambda MP prime is just lambda MP plus 1/2. So as you can see from this, yeah, they are, I mean, closely related, of course. Okay. After localization on the square function and some discretization, the LP estimate for Stein's square function can boil down to the following estimate. So here SQF is a discrete type. Oops. So here SQF is a discrete type of square function, which is defined as the following. Yeah, so each SGF is basically a smooth Fourier restriction on the annulus of radius 1 plus j of r. So for each SGF is supported in this kind of annulus. It has radius 1 plus j over r, and it has thickness, which is r to the minus 1. So to define this discrete square function, we need to consider all the annulus like this. So there are roughly R many annulus. Okay. Yeah, so this is basically how I try to understand the square function. So it's a collection of annulus. So you need to take care of a collection of annulus. They are all neighborhood for that's the, I think that's the better way to understand it. Let us do a little comparison. So we made a comparison between the Stein square function, which is this, or let's call it the discretized square function, and the following square function for congruent boxes. So here is another square function where Q is collection of congruent rectangular box. So Q look like this. They just like a tiling of Rn. So all of them, they are congruent. And phi Q is just like a smooth kind of function on Q, phi Q head. Yeah, so these two square functions are quite similar, except that for this square function is supported in a neighborhood of a curve of a geometric object with a positive curvature. But as you can, this square function is supported in the neighborhood of a plane, so there's no curvature on the plane. Yeah, and for this square function, Cordova proved that for any p greater than 2 and less than infinity, this square function is bound in LP space. So there's a loss for the LP boundedness of this curved square function for certain p, and the loss possibly is due to the curvature of the spheres. So when you have curvatures, things they will go bad. Okay. Now let's look at some application of the LP estimate for Stein's square function. So suppose that we can prove the following LP estimate for p greater than Pn, so greater than this endpoint, and also in a sharp range of lambda. Then it follows that the Bochner Riesz operator is bound in LP space, as well as the maximal operator in the same range of p, and in its sharp range of lambda. And basically, when p greater than 2, Stein's square function will imply maximum Bochner Riesz, which in turn imply Bochner Riesz, and that's the storyline. Okay. One other application on Stein's square function is estimates for the local smoothing problem for fractional Schrodinger equations. So let's first introduce the local smoothing problem. Suppose alpha is some number bigger than 0, and we consider the following PDE. And the case alpha equals to 2 corresponds to the Schrodinger equation, and the case alpha equal to 1 corresponds to the wave equation. And actually for Schwarz function G, the solution of this PDE has an explicit formula. It looks like this. And this formula is very similar to the extension operator. So if we view this guy as the fractional Schrodinger operator, and it is defined as this. And now for the extension operator, it is defined as, so for the extension operator for the surface C to the alpha, the operator is defined as this, 2 pi I x dot C plus t c to the alpha. So as you can see from these two expressions, the only difference is, oh, sorry. I think, yeah, we don't have a hat here. So the only difference is where's my pen? Yeah, wait. Okay, now I can draw. The only difference is this guy. So for the restriction problem, we are looking at G. But for the Schrodinger operator, we are looking at G hat. In terms of expression, this is the only difference. Yeah, let me, how do I clear? Okay. Now, if we denote the standard Bessel potential space by W beta P, and for simplicity, we define the vector beta C as the following. So it satisfies this equation. Then the local smoothing conjecture for alpha not equal to 1 is that for any P greater than this endpoint, 2n plus 1 over n, it holds the following W beta P to LP estimates for any beta greater than the endpoint beta C. So beta is also a regularity factor. Okay, for the wave equation, the exponents are a little bit different. So if we define beta W as some guy satisfy this equation, then the local smoothing conjecture for wave equation is the following. So there are two differences. The first one is that this exponent is bigger. So for the case alpha not equal to 1, the exponent is this. And the second difference is this guy. For the case alpha not equal to 1, the regularity equation, the right-hand side should be n times 1 over half, 1 over 2 minus 1 over p minus 1 over p. Oh, yeah. So these are the two differences. And actually, why this factor is smaller, as you can see, is one-dimensional less. It is because for the local smoothing problem for wave equation, you're actually looking at the geometry object is a cone. But for the other fractional Schrodinger equation, let's say alpha equals to 2, it's a paraboloid. So for cone, there's one-dimensional flat, but for paraboloid, there's no dimensional flat. So that's why for cone, you have one-dimensional less in this the range of P. And how do I clear? Okay. Yeah, and local smoothing conjecture are closely related to the restriction problem. In fact, we know that the n plus 1 dimensional local smoothing for wave equation will imply the m-dimensional Bochner Riesz problem conjecture, and which in turn will imply the n-dimensional spherical restriction conjecture. And also, Rogers showed that the n-dimensional restriction for paraboloid, here I should mean for paraboloid, will implies the n minus 1 plus 1, which is just n, dimensional local smoothing for the Schrodinger equation. And for the other side, for the opposite side of this claim, here's a reference by Lee, Rogers, and Seeger in JMPA. They discuss something about the other direction. Okay. So for Stein square function, it actually implies some results to the local smoothing problem. So here's the corollary. Suppose that we have this LP estimate for Stein's square function at the sharp endpoint of lambda and when p greater than the endpoint Pn, then for any alpha greater than 0 and beta c satisfy this equation, we have the following estimates. And here's a little remark that beta c is only sharp, it is sharp unless alpha equal to 1, which corresponds to the wave equation. So as an application, Stein square function only can give some sharp result for local smoothing other than wave equation. For wave equation, it would give some result, but it is not sharp even for the regularity factor beta. Okay, now let me state our result. So the first one is for square function. So if we denote by Pn the smallest exponent obtained by Hickman Zhao in their most recent restriction paper, and this Pn is also the best exponent that the restriction has been verified in higher dimensions. Then our main result is that for any p greater than the Pn, we basically verify the LP estimate for Stein's square function at the sharp endpoint, sharp range of the regularity factor lambda. Yeah, as mentioned about this result on Stein's square function will imply certain estimate for the local smoothing problem for the fractional Schrodinger equation. But actually, for some range of alpha, we can do even better. So when n equal to 3, for any alpha exact 1, and for n bigger than 3 and alpha greater than 1, we can prove that when p greater than Pn plus 1, then we have the following estimate for the fractional Schrodinger operator. Let me call it. And compared to the previous result given by Stein's square function, here we prove the range p greater than Pn to p greater than Pn plus 1. So yeah, that's actually the improvement when alpha greater than 1. Actually, for alpha equal to 3, we get the range 3.25, which is basically it's better than what Stein square functions can give, I think. Okay. Let me clear. Now let me give a sketch of proof on both of our results. So for simplicity and to help you digest our main idea, we just take n equal to 3, and we restrict our discussion in R3. So here is some basic reductions. So let's first recall our target operator, which is this discretized square function. And by the triangle equality, we can assume that all this this Fourier multiplier, they are supported in a conic region. So they are basically supported in this conic region. So yeah, so any line in this conic region, they are transverse to the horizontal plane. Okay, and clear. Okay, next we will perform a Bougainville's type of broad narrow reduction on our square function. We define a factor t, we define factor k, which is very small, comparable to R. And we partition the unit sphere using caps of dimensional k to the minus 1. So basically tau is like a square with side length k to the minus 1. And then we define the square function associated tau by this. So basically, each mj tau is a Fourier multiplier, which is the portion of mj restricted to the ring to the region of tau. So let me draw a picture here. So this is the whole mj, and this is some region that the directional cap tau can determine, and mj tau is basically some smooth function supported in this region. Okay, let me clear. Okay, we use this K inverse cap to define broad narrowness as always, but we cannot use induction on the narrow part, since it is hard to find the parabolic scaling that works for all multipliers mj tau. Well, the thing is that if you have one small neighborhood of an annulus, which corresponding to the Bochner Riesz problem, then you can find a way to rescale so that you can make this guy. So this here is k to the inverse 1. You can find a rescaling so that you can rescale this guy to some other neighborhood of some surface with positive curvature, and this range is 1. Okay, so for one cap, you can definitely do that. The thing is that for square function here, we have we have r many this annulus in the horizontal direction. So for us, it's hard to find such a rescaling that works perfectly for all this annulus. So basically, we don't go into this direction to use broad narrowness. Yeah. Instead, we just iterate on the idea of broad narrowness on each narrow part on this narrow function, and define a second level broad part and narrow part corresponding to a cap tau. So basically, this is a cap tau. The side length is k to the minus 1, and we covered it again using smaller. Okay, let me just draw some of them. Some smaller cap. Each of them has side length k to the minus 2, and in this way, with this new smaller caps, we can define the broad part and narrow part with respect to this k to the minus 1 cap tau, and let's call this the second level broad narrowness. And somehow we can iterate this idea, and we stop at L step where k to the L equals to r half. So when our iteration stops, there will be no curve, and everything is flat. So we don't need to do broad narrowness anymore. And when the iteration stops, we will have broad function at many different levels. And the argument for all these broad functions are essentially the same. So to save us from abundant notation, let's just assume that the square function itself is a broad function at the first level, and after some standard localization, we only need to show this local estimate, where B is any arbor in R3. Okay, clear? Okay, the first tool we use, there are mainly two tools we use. The first one is polynomial partitioning. So polynomial partitioning basically help you, it's a method developed by Goose and Katz to solve the Erdős distance problem, and later was bring to the study of oscillatory integrals operators by Goose. So basically, Goose used polynomial partitioning to give some significant improvement on restriction problem. And polynomial partitioning roughly allows you to break down something. For instance, here is our square function, so that when you break it down, each pieces, there are some algebraic property that was remain. So when you break down, you don't break anything. There's still some algebraic property among all those pieces. I will not state the polynomial partitioning here. I will just state the conclusion from polynomial partitioning. So we used it iteratively to break down the LP norm of the square function. And when the iteration stops, we will have a collection of cells. Let's assume the scale is rho. And some functions, let's call cell functions, associated to each cell, and a broad estimate. Okay, each cell function has certain algebraic property. This is just part of it, but this is something we will use. So basically, the cell function is concentrated on wave packets that are essentially supported in the same neighborhood, which the thickness is rho to the half, of a low degree variety inside the ball B-roll. Yeah, as mentioned, this is not the only property, but this is the main information we will use in our proof. Let me clear. Okay, this other main method we use is polynomial Wolff axiom. So polynomial Wolff axiom roughly says that there cannot be too many tubes in the same neighborhood of a variety. And here is a quantitative version of the result. So suppose that Z is a semi-algebraic set, which you can just think of as a variety inside a ball. And suppose that Z is contained in the ball B row. We let TZ be a collection of tube, which is something like this. So you have radius rho half and length rho. And all these tubes are contained in the same neighborhood of Z. Then the number of distinct direction of tubes in TZ has an upper bound, which is some constant depend on D, and the main term is rho half. So actually for all the collection of tubes like this, the possible directions of sets, so each tube, each this kind of tube, it corresponding to a directional set in, let's say this is S2, the unit sphere. So for this tube, it corresponding to some cap on the unit sphere with radius rho to the negative half, and whose center here is basically the direction of this tube. So let's call this guy the directional cap of our tube. And as you can see from its definition, if we just consider all those collection of tube like this, then the possible number of direction is something. It is just rho, because for the unit sphere, it contains rho many caps of radius rho to the negative half. So polynomial Wolff basically says that when you restricted all those tubes inside a same neighborhood of a variety, then the possible number of directional set is severely reduced to rho half. A good way to think about it is if you have a plane. Basically, you take Z to be a plane, and here is the rho half neighborhood of the plane. You consider all the possible tubes lie inside this plane, and you will see that the number of possible directions is just rho half. Okay. Now, this result was proved by Goose in R3 and by Katz and Rogers in higher dimensions. Here's a little remark. The constant CD can be as small as some polynomial of D in R3, but may be very large, larger than D to the D to the D in higher dimensions. So basically, when in higher dimensions, the constant depending on D is pretty bad. Okay. Polynomial Wolff axiom is very useful in restriction problem. Let's briefly explain it in our notations. So recall that each of our cell function is concentrated on wave packets in this same neighborhood of some variety 0. And polynomial Wolff axiom basically tells us that the directional set that make contribution to this cell function has mass roughly go to the negative half. By this, I mean, so all the possible directions are rho half. Sorry, I mean, all the direction that is restricted to the same neighborhood of variety is rho half. And all possible directions for any tubes is rho. So the ratio is rho to the negative half. So that's what I mean by mass. And yeah, so this roughly says that only a small portion of F hat, which has the same ratio here, will make contribution to this cell function. And the above argument remains valid if we replace this operator, square function operator, by the extension operator. So we can also work on the extension operator and do the same type of argument. And we'll find that for each cell function EFO, only a small portion of F hat will make contribution to this cell functions. And this will lead to some non-trivial result on the for a restriction problem. But however, the information on the directional set essentially give information on F hat. It does not say much on F. But in Stein's square function problem, as well as the local smoothing problem, we are looking at F rather than F hat. So to get around this difficulty, a crucial observation here is that similar to the restriction case, we can prove that only a small portion of F will make contribution to each cell function. And the ratio is exactly the same ratio as restriction problem. And this is based on a different type of polynomial Wolff axiom, which focus on the support of tube. So when the support of tube is corresponding to F, and the directions of tube is corresponding to F hat. Okay, let's be more precise. So we first introduce a definition about tubes at different scales. So yeah, so for a tube, we define directional set as a rho to negative half tube whose center is direction of T. This we just talked about it before. And we consider two tubes, T1 and T2. Each is at scale rho 1 and rho 2. And we define T1 is smaller than T2 if first, T1 is contained in T2. And second, the directional set of T1 contains the directional set of T2. Yeah, that's basically two restrictions we made on T1 and T2. Now we can state our the polynomial Wolff axiom that concerns the locations of tubes. Yeah, so same setting. Z is a self-semi-algebraic set with degree at most D. It is contained in a row called B row. And we define T0 to be the collection of tubes that is contained in this same neighborhood of a variety. Now we define a collection of bigger tube. So bigger tube is basically says that, suppose that this is Z, and this is the same neighborhood of Z, and this is some small tubes. And we consider all those larger tubes look like this. So the larger tube belongs to TZR if and only if there's a smaller tube in T0 such that T prime is smaller than T. Okay, now we can, let me go back. Yeah, now let's consider the union of all those bigger tubes. So basically this is the union of bigger tube. Let's call it X. And then the result, the polynomial Wolff basically says that X has an upper bound, which is R cubed times the saving rolled to the negative half. Okay, let's think about if we don't have any restriction on TZR, so we consider all the possible big tube in R3, then their union can be as large as R cubed. So polynomial Wolff basically says that if you have this section, so basically each bigger tube is bigger than some smaller tube, then you will have a saving with ratio roughly is rolled to the negative half. And you should compare this to the previous polynomial Wolff. Okay, let me clear. And in fact, something stronger is also true. Let X be the set above, as above. Suppose that all the directional set of T is contained in the vertical direction. Say in a vertical cone. So basically, T is always transverse to the horizontal plane. Then if we consider any horizontal plane, and we look at the intersection between this plane and X, then this guy as a two-dimensional object is measured also has a saving, which is rolled to the negative half. Yeah, so basically this is stronger than the previous one, because if this is true, then we can just integrate in the vertical direction and we will get the previous result. Okay. And the sliced version was implicitly proved by Zhao in any dimensions. And in R3, an R3 version with better constant on D was proved by myself in my first Bochner Riesz paper, which I just follow Goose's idea using hairbrushes argument. Okay, now we can complete the proof. So recall that each cell function is concentrated on wave packet in some same neighborhood of a variety. And hence by polynomial Wolff, there's a set XO such that its measure is bounded above by some factor. So we have a saving rolled to the negative half here, so that only those F is restricted to this set will make contribution to this cell function. So it means that if you look at F, those F whose support is outside this set, then it do not make contribution to the cell function. And this is strong enough to help us complete our proof in R3 for the Stein square function. As for the local smoothing problem, we just replace the square function operator by the fraction Schrodinger operator and repeat the similar argument as above. And we use the sliced version of polynomial Wolff so that we can also find a set XO in R2. And it has an upper bound with a saving rolled to the negative half, so that when only F restricted to this set will make contribution to this cell function. Yeah, and this basically help us complete the proof of local smoothing problem in R3. But the argument in higher dimension is pretty much similar, but much more complicated, I would say. We also use polynomial partitioning iteratively, and instead of using polynomial Wolff, we use a refined version of it, which is called nested polynomial Wolff. And this result, the result we need for nested polynomial Wolff is also implicitly proved by Zhao, and so as the slice version. And this basically helps us to complete the proof in higher dimensions for both Stein square function and the local smoothing problem. Okay, thank you.
Okay, thank you for a really nice talk. Are there any questions?
Hi, Shukun, this is Saurav. So, like in dimension 3, this range happens to be same for maximal and Bochner Riesz as well, or?
You mean dimensional 3?
Yeah, the improvement you have obtained, is it for the same kind of exponent Pn for all the 3 years?
In which operator?
Like square function and maximal function, Bochner Riesz, and then the Bochner Riesz means for single scale.
Yeah, they are all the same points, 3.25.
Including the 3.25, correct?
Improving the what? Sorry.
The 3.25 is included in that range.
No. We only get 3.25.
Okay.
The previous best range, I believe, is the bilinear range.
All right. Yeah. Okay. Thank you.
And so, can you also use these kind of methods to prove Bochner Riesz for, like here you have mod of xi squared, right, inside? So instead of that, you have a different function of xi, different homogeneous function of xi with some homogeneity and some more conditions.
Let me move to I'm not sure I understand what you mean. You mean this guy?
Yes, I mean, I'm saying the Bochner Riesz, which you considered in the beginning. Right? So there you have this function 1 minus mod of xi squared divided by t squared, right? So instead of mod of xi squared, I'm saying, can one take a more general function of different homogeneity?
Yeah, maybe it works. I mean, here the reduction is you do some kind of Winnick decomposition approach to its singularity, which is at a unisphere. I don't know. I never think about that, but probably it works.
Yeah, and there's some conditions on the surface where it is equal to 1. I think Laura Cladick, she has some results in dimension 2, I think.
Oh, yeah. Okay. I should take a look.
Okay. Yeah, if there are no more questions, then let us thank Shukun for a very nice talk. You can unmute and clap, or yeah, you can. I'll definitely clap for this. So thank you for a really good talk. Yeah. Okay, I'll stop recording.